So our motivation is based on, ammonia detection is important for many applications, but we initially started out looking at for power transformer failure, but also important is for health and safety. Quite recently, 3 people died because of an ammonia leak in an ice rink in Fernie, British Columbia. Another motivation is that through the use of Vapochromic coordination polymers, we can then possibly miniaturize these sensors to be field deployable or even wearable. Now, vapor coordination polymers, or VCPs, are a class of compounds whose fluorescence emission shifts in the presence of a target gas, and in our case, it's ammonia. Now, the challenge for using VCPs as a sensing thing is that you need to mobilize it in a high surface area to volume ratio. Previous work that had been done involved brominating the VCP, which makes it soluble and spin coatable. However, this is a lengthy and difficult process to trigger the total elimination of the bromine, and even partially brominated VCPs do not fluoresce. So our approach, we decided to employ polydimethylsiloxane, or PDMS, as the mobilization surface because it is well understood and easy to micropattern. It's also compatible with existing microfluidic systems. For our examination of how to immobilize, we chose 3 different methods. Firstly, a flat or unpatterned PDMS surface, and then using post arrays in PDMS either through simple or mushroom shaped. And through the cross section, you can kind of see the difference here. Using the post arrays may facilitate both mechanical and van der Waals adhesion. In our design, both the simple and mushroom post designs were to be 10 microns in diameter, spaced 20 microns center to center, with a 20 micron post height. So in our fabrication process for both the simple and mushroom post arrays, we followed what was outlined by Samiotto et al., where we started off with a silicon wafer and coated that with a chrome gold adhesion layer for the photoresist. Now, then we spun on polymethyl glutamide, or PMGI, which is a deep UV positive photoresist. Now, the difference between either creating a simple post array or the mushroom post array is that at this step, if you want to create the simple post array, you immediately go on to the spin coating of the AZ9260. However, if you want to create a mushroom post array, you need to expose the PMGI to 254 nanometer UV light. And for our experiments, we experimented with between 200 and 300 millijoules per centimeter squared. At this point, we spun on the AZ9260 photoresist, exposed it, and developed. And then once it was developed, we mixed the PDMS 1 to 10 and poured into the mold. It was cured at 50 degrees for 12 hours and then further hardened at 120 degrees for 30 minutes. At this point, we demolded the PDMS post array from the wafer, and as the final step, we took the VCP and mixed it with ethanol through the use of a pipette and created a suspension, and then immediately drop cast that onto the post array. So for our experimental procedure, we placed the VCP and PDMS sensor inside a quartz cuvette, and we repeated the experiment with the flat, the simple, and mushroom post arrays. We also took a control sample of the un-immobilized VCP sample to test as well. This was exposed to ammonia gas flow, where we used headspace ammonia at a concentration of 50,000 parts per million with a flow rate of 300 cc's per minute. And as a control, we also exposed all these samples to pure nitrogen gas flow of 1,000 cc's per minute. These samples were then fluoresced with a 405 nanometer blue laser, and the responses were recorded using a spectrometer. So, as for results, on the left-hand side in Figure 2, he just showed the simple post array, of which it came out pretty close to the design specifications. And in Figure 3 on the right shows a simple or slight mushroom cap post array that was formed when the PMGI was exposed to 200 millijoules per centimeter squared of 254 nanometer UV light. So in this slide, we see how the VCP has been immobilized within the post array. With Figure 4, it's the simple that kind of relates to the Figure 2 in the previous slide, and Figure 5 is the immobilization that has occurred on the mushroom posts that were formed when the PMGI was exposed to 250 millijoules per centimeter squared. Now, there was, of course, variation in the mobilization as you went over the sensor surface, but the immobilization that you can see here was typical of what was observed between mushroom post or mushroom shaped and simple posts. So looking at the fluorescent response, in this first slide, we see that it peaks using the control sample that we used as the baseline at about relative intensity of about 2,250, centered around a wavelength of 525. So next, we see the results of the VCP that has been immobilized on the flat PDMS surface. So the important things to take note of here is that the peak intensity here occurs 60 seconds, which is about 6 times longer than with the control sample. But the most important takeaway is that after 60 seconds, we start to see a decrease in response, indicating that the VCP is starting to be removed from the sensor surface due to the ammonia flow. When we compare this to the simple post array, again we see that the time frame has increased even more for 100 seconds or 10 times longer than control sample, but the peak intensity kind of matches what the control sample was. Now, as we got more proficient at the fabrication process, we decided that it would be a good idea to rerun the simple posts. And from here, we can see that we've managed to drastically reduce the response time down to that equivalent of the control sample, and that the peak intensity again is equal or actually above to what the control sample was. Now, I should mention that we've changed the y-axis range from the higher end of 2,500 to 3,500 to reflect the results that we observed from the mushroom post arrays. And here we can see from the mushroom posts that with the mushroom posts formed from 250 millijoules per centimeter squared, we see an increase of relative intensity from the simple post by about 500, but 750 above what the control sample was. Whereas when we look at the 300 millijoule per centimeter squared, we see an even greater relative intensity increase to about 800 or 1,000 above the control sample. So, in conclusion, we have found that both simple and mushroom-shaped PDMS post arrays show a significant improvement over flat PDMS surfaces for the immobilization of VCPs. We also see that increasing the mushroom cap size or diameter appears to possibly aid in the adhesion of VCPs and improve response. So some of the future work that we want to look at doing to see what the effects are is to, one, change the physical post geometries or the size and spacing and compare. Also experiment with mushroom cap sizes and see the effect on adhesion and response. All of the work the testing that we've done thus far have not introduced any kind of surface treatments. So that is something that we want to look at and see if that helps with creating a better adhesion. Also look at lowering the ammonia concentrations, for example, 1,000 parts per million. We have done some initial testing where we haven't presented the results here, but it looks very promising. And also to look at integrating it with a microfluidics device, and that was in our design phase. I'd like to finally acknowledge IEEE Sensors Committee for inviting me for this talk, National Science and Engineering Research Council of Canada, the members of our microinstrumentation lab, members of the Leznoff and Chapman research groups, and 4D labs and engineering microfabrication facilities. Thank you.